Okay, so in the last video we were looking at vectors, and now we're going to talk about the limits and differentiability of a vector value function. So just as a reminder, if we wanted to talk about something's position, let's just say like something's um, some object's position at any time. We liked thinking about it in terms of a vector because it let us split up its x direction. So we could have like some function that depends on time in the x direction. So we notate that with I, because I is in the x direction, plus um, some function g of t in the j direction. So the I and the j are unit vectors in the x and y direction. Um, and now what we want to talk about is the limits and differentiability. All right, so first thing to define, if we have some vector value function, the limit as t approaches a of that function is just it's the limits of each independent function. So it's the limit as t approaches a of f of t in the I direction, and the limit as t approaches a of g of t in the j direction. So we can treat each function independently under the provision that provided that both of these functions have limits at that value. So for example, let's do this problem here. We've got some function r of t, which is defined as cosine of t in the I direction, plus sine of t in the j direction, and we want the limit as t approaches pi over 2. Well, this is a pretty easy limit to find because both of these functions are continuous everywhere. So the limit as t approaches pi over 2 is the same thing as just the function evaluated at that point. So we're talking about cos of pi over 2 in the I direction plus sine of pi over 2 in the j direction. And this is just a reminder on limits that, as long as a limit is continuous and defined over that interval, you can just evaluate, to evaluate the limit, you can just evaluate the function at that point. So we know that cos of pi over 2, because we know our unit circle, is 0. So this is going to go away. And then the sine of pi over 2 is just 1. So we get left with 1j. And so just as a reminder, that what that looks like, that's a vector of length 1 in the y direction or in the j direction. So something like that, where it's of length 1. All right, so what about derivatives? Well, this is a formal proof. And if we just sort of jump down to the bottom, let's just say that we can take the derivatives of each function independently. And remember, this is coming from our function where r equals f of t at I plus g of t at j. And if we go through the proof, it's worth the reminder. What we're doing right here is the limit definition of derivatives. So what I'm squaring in right now, that's just the slope. That's r of a plus h minus r of a over h. So just as a, if we sort of think about, just as a reminder of what that important equation is if we have this function here, and um, we have some point a and some point a plus h. At that point a, this would be the point r of a, and here at a plus h, that's going to correspond to r of a plus h. And what we're finding here is just the slope between those 2 points. This is just the slope, and as if we let h approach 0, these points are getting infinitely close to each other. So that slope becomes the derivative. So as we go through this, you can spend some time looking at this, but all we're doing, we're evaluating each um, each of the vectors f of a plus h at I plus g of a plus h at j. That's just this value here. And then this, maybe this will be helpful. Um, that is that. This is this. And then we just can our um, reorganize this statement and say f of a plus h minus f of a, and g of a plus h minus g, that's here. And then what we notice, this is just the derivative of f at a, and this is just the derivative of g at a. And so we get our a formal proof that the derivative of a vector valued function is just the derivative of each of the respective functions. So now let's apply that. So let's just practice that new skill. We're given some function, some vector valued function r of t equals cos of ti plus sine of tj, and it says find the derivative function. Well, so the derivative function r prime of t is just going to be the derivative of each of those respective functions. So the derivative of cos of t is negative sine of t, and that's in the I direction, plus the derivative of sine of t, which we know is cos of t, and that's in the j direction. So that's the derivative function. Easy. It's totally easy. So now let's do some application of this, and let's do some physics application. So we're given this. We know this about position, that if we have position, then the derivative of our position is the velocity, and the double derivative, or the derivative of the derivative, is the acceleration. Those are physical applications that you should be familiar with, and if not, maybe take a little bit of time to do a little research on the World Wide Web, or the information superhighway, looking at physics terms, velocity, acceleration, and position. But I'm assuming that you guys are familiar with that. So it says a particle travels in the plane so that the position, so we're given the position function right here. It's given by, it's given by this function, and we're looking at this interval. So the question is, determine the speed of the particle at t equals pi over 4. So we're looking for the speed. So let's find a velocity vector. We know that r prime of t, well, let's take the respective derivatives. The derivative of t is just 1, so we have I plus, well, the derivative of ln of function, we're going to have to use the chain rule. So the derivative of ln is 1 over the function. And then we take the derivative of the function. Um, so we have to remember what the derivative of secant is. Well, if you don't remember it, I like to think of that as cosine to the negative 1 of t, and then I use the power rule. So we have negative 1 times cos to the negative 2 of t times the derivative of cos, which is negative sine of t. And that's all in the j direction. All right, so now let's evaluate at pi over 4. So r prime of pi over 4 in the x direction. Well, the x direction, it's a constant velocity. It's just 1I plus, well, 1 over secant is just cosine. So we have cosine of pi over 2, or sorry, pi over 4. Um, these negatives that we have here will cancel each other out, so we can just forget about them. So then we have times cosine to the negative 2 pi over 4 times sine of pi over 4. Now, these will simplify really nicely for us. This will get us to, well, we know cosine, oh, I forgot to put a j over here. We know cosine of pi over 4 and sine of pi over 4 are both root 2 over 2. So the first one, root 2 over 2. And then we have cosine to the negative 2. So that's going to bring it over here under the axis. So root 2 over 2 squared. That's this term. And then times sine of pi over 4. Well, that's root 2 over 2. And that's all in the j direction. And we can simplify that very simply. And we get that this derivative equals I plus, well, this is all going to simplify to 1. So I plus j. Now, that's the velocity vector. And what that looks like is a distance of 1 in the I direction or the x direction, a distance of 1 in the j direction or the y direction, and then this corresponding, this is the actual velocity. So to find out what that velocity is, we're going to need to use Pythagorean theorem. And to maybe extend this out in a general case, we know that speed, which is different from velocity in that it doesn't have direction, is the square root of well, it's the square root of each of those respective derivatives. So let's say r prime of t in the x direction plus r prime of t in the y direction. So for this particular problem, it's going to be the square root of 1 squared plus 1 squared, which is just root 2. So that's our speed. Okay, now let's work the other way. So now in this example, instead of given the position, we're given the acceleration vector, and we're given some information about our position and velocity at time equals 0. So we know at time equals 0, our position is at 0 comma negative 1, and the velocity is negative I. So it says find the position at time equals 2. Well, so we're going to need to do some integration. So we know that the velocity equals the integral of the acceleration. So it's going to be the integral of 12t I plus 2j. And when we integrate this, integrating each, let's be totally good. Let's put a dt. We're going to integrate each vector value independently. So 12t integrates to 6t squared in the I direction. Now 6t squared plus c in the I direction plus 2 is going to integrate to 2t plus c in the j direction. Now we need to find out what each of those values are. We need to find out those c values. And just to, I think to make it a little bit clearer for us, let's call this c sub x and this c sub y. So to find c sub x and c sub y, we can plug in what we know about the initial conditions. And so let's plug in what we know about the initial conditions. We know that at time equals 0, we know that at time equals 0, our velocity is negative I. So we know that 6 times 0 squared plus cx I. So I'm just putting in, so I'm putting in 0 into my velocity or my r prime function. So plus 2 times 0 plus cy j. That's my, this is my velocity at time equals 0, and we know that it should be negative I. So now let's solve those each independently. So um, this becomes cxi plus cyj equals negative I. So since there's no j term here, we know that cy must be 0. And since we know that cxi must equal negative I, that makes it clear that cx equals negative 1. Okay, so now we know our constants, and we're going to do some more integration. But let's just write out what my velocity vector is, and then we'll, on the next page, figure out what my position vector is. So my velocity, which is the derivative of my position, equals 6t squared minus 1, that's the constant that I just found there, in the I direction, plus 2t plus 0, and that's the constant I found for cy in the j direction. Now I'm gonna use this equation here that I just found, and I'm gonna integrate that to get a position curve. But let's do that on the next page. All right, so to find my velocity, well, I've already found my velocity vector. So to find my r vector, my position vector, r is going to be the integral of my velocity, or r prime. So it's going to be the integral of 6t squared minus 1 dt. Oops, let's not do dt yet. I plus 2tj dt. So when we integrate this, this is going to equal 2t cubed minus t plus some new constant cx in the x direction, plus t squared plus constant y in the j direction. And then we're going to need to give our initial condition right here, which is that at time equals 0, we know that I'm at the point 0 comma negative 1. So at time equals 0, plugging in 0 here, we get cxi plus cyj. And then writing this in terms of writing this value in terms of a unit vector, that's just 0 I minus j. So similar to the last one, since we have cxi equals 0i, we know that cx must equal 0, and cyj equals negative j. We get that cy must equal negative. Oops. Let's make that look a little bit nicer. So we get cy must equal negative 1. So now that we know my constants, the rest is pretty straightforward. Let's put in my constants, and then let's evaluate for the position at time equals 2. So um, after doing these 2 stages of integration, I get that my position function equals 2t cubed minus t plus 0 I. And I didn't need to put the 0, but um, just so that just to put it in there. Plus t squared minus 1 j. And now let's evaluate at t equals 2. So we want to find the position at t equals 2. So we're looking for r of 2, which, as we evaluate this, 2 times 2 cubed minus 2i plus 2 squared minus 1j. And so we can simply do that. 8, 16 minus 2. So we have 14i plus 4 minus 1, so 3j. And that's my position at time equals 2. So 14 in the x direction plus 3 in the y direction. All right, so one more of these problems. Now working the other way. So we're given the position, and we're going to find the velocity and acceleration vectors at time equals 2. So, what I would do if I were you, pause this video, find out, do this on your own, and then start the video just to make sure you got it right. But I think at this point, this is pretty straightforward calculus. So to find the velocity, and pause it if you haven't already. Try it on your own, and then unpause it. Welcome back. So velocity equals r prime of t, which, if we take the derivative of each of these, that just becomes ti plus j. And if we take the derivative of that, acceleration is r double prime of t. What we're left with is the derivative of t is just I, and the derivative of 1 is 0, so it's just I. I want to make that. That looks nicer. So we have the velocity, which we got from taking the derivative of the position, and then we have the acceleration, which we got from taking the derivative of the velocity. And now we want to just find r2, r prime of 2, and r double prime of 2. So r2 going into our original function is 1/2 times 2 squared I plus 2j, which is 2i plus 2j. And what does that look like? Well, that's going to look, that's 2 in the I, 2 in the j. So it's going to be some vector like that with a 45-degree angle here, or a pi over 4 radian angle there. And my velocity, well, that's r prime of 2. And using this equation, that's going to be 2i plus j. And what is that going to look like? Well, that's going to look similar, but the y value won't have the same amount. So this function, or this vector rather, will be 2 in the x and then only 1 in the y. So the corresponding vector, the net vector, will look like that. And lastly, we've got the acceleration vector. So the acceleration vector is our double prime of 2, and that just equals I. So everywhere, no matter, it's independent of time, our acceleration everywhere is just the unit vector I, which has a length of 1, and it's all in the positive x direction. So that's that's looking at limits and derivatives of vector valued functions. Hope this was pretty straightforward. That's it.